Hi, everybody. This is the podcast for Kepler's Laws of Planetary Motion. We actually already did 1, 1b, and 2 yesterday, so we're just going to sort of skip over those. But let's do a little quick reminder of what Newton's Law of Universal Gravitation said. By the way, this goes with worksheet section review 8.1 and all the problems you have for homework regarding that. So Newton's Law of Universal Gravitation says that the gravitational force, remember that we denoted that with a F sub G, is directly proportional to, now we used big G yesterday, that's 6.67 times 10 to the negative 11, but the gravitational force is directly proportional to the product of the masses. So once again, if you double your mass, you're going to double your gravitational force. If you triple your mass, you're going to triple your gravitational force. But it's inversely proportional to the square of the distance between those masses. So if you double your distance, you got to remember it's 1, I'm going to double my distance on the bottom, but that distance gets squared, so your force of gravity would be 1/4 the amount that you would have if you doubled your distance. So that's what Newton's Law of Universal Gravitation explains. Kepler, he took Newton's laws of universal gravitation and made 3 laws of planetary motion from them. The first one simply states this, that all the planets have orbits that are ellipses, like you see right here that I drew this ellipse, and the sun is at the focus of the ellipse, and then there's a random point over here at the other, which is equal distance from the sides. So however far the sun is from that part of the axis is same over here. Okay? There's really nothing there, but you can sort of tell where it is based on how far away the sun is from it. Now, the second law, feel free to stop this at any time. The second law says if you take a line and you draw it from the sun, which I have labeled as a star, I drew a line from the star here to the planet that's going around that star, that these lines will sweep an equal distance in an equal time. So let's just say that the planet goes from here to there in 1 month. Well, that means that this area over here, and the planet goes around this distance here, that's also 1 month. But it's not the distances that are equal, it is these areas that are equal. So even though this looks like a bigger area right in here that I'm coloring, it's actually the same area as this one over here. This one's just thinner and longer, this one's shorter and thicker. Okay? So the planet, in order for it to cover a greater distance, but same area, it has to go faster. So when you're closer to the sun, you move faster. And that faster speed equals more kinetic energy. So you have more kinetic energy when you're close to the sun, but less potential energy when you're close to the sun. This is called perihelion. Helion or helios is Greek for sun. Peri means close, or perihelion begins with P, and so does pretty darn close. So when you're pretty close to the sun, you're at perihelion. Here you're at aphelion. Aphelion means you're away. Aphelion begins with A, and so does away, so it's away from the sun. So here the speed is slow. Velocity is slower. So therefore, you have a decrease in potential energy, but in kinetic energy rather, wrote that down wrong. But you have an increase in potential energy. And that's what the second part, number 4, says down here, is that the total energy of the planet is always conserved. So as Ke increases, Pe goes down. But if you add them together, you always get a constant. As the planet gets farther from the sun, Pe increases, but Ke decreases because the speed's slower. So planets travel faster when they're closer to the sun, So kinetic energy increases, but potential energy decreases. What I want to show you in this particular example here, so if you notice the planet, as it comes closer to the sun, the red line or the velocity vector gets much, much greater. So it's like throwing a ball up in the air, actually. So at the top, you have very little kinetic energy, lots of potential energy. The potential energy becomes kinetic energy as the ball comes back down towards the ground. So instead of a ball going back down to Earth, I have the Earth coming back down towards the sun. Once again, the total energy always has to stay the same, but potential and kinetic energy are constantly swapped in places. Now for the third law of planetary motion, I'm going to say the formula instead of the actual law. So I'm going to have the period, which is the time it takes the first planet to go around, squared over the period it takes the second planet to go around, squared, has to equal the distance from the planet to the sun, cubed, this is the first planet, over the distance of the second planet, cubed. And to make the distances equal, easy rather, we're doing number 6. We're going to use what we call astronomical units. An astronomical unit, or an AU, is the distance from the sun to the earth. So 1 AU equals the distance from the sun to the earth. And we're going to use AUs in these formulas instead of actual meters. Just makes it easy. So let's do this next one here. Very, very easy problem. If I want to know, it takes Jupiter 12 years. That's the period of Jupiter to go around the sun. Use Kepler's laws to calculate how far, which will be the distance of Jupiter from the sun. Well, I'm going to use this formula up here, but instead of 1s and 2s, I'm going to put the period of Jupiter. I'll square that. And down here, I'm going to use the period of the Earth, because the Earth is something I know, first of all, and if I use AUs, it's going to make it really, really easy to do. This will be the distance Jupiter is from the Earth's cube. This will be the distance Earth is from the sun, cubed, both in AUs. So let me put the stuff I know. I know that period of Jupiter, this right here, is 12. I'm going to square that. Earth's period is 1 year. It takes Earth 1 year to go around the Earth's sun, so I'm going to square that. The distance of Jupiter is what I'm trying to find, so I'm going to put cube next to b sub j. And then I'm going to have the distance Earth is from the sun is 1 AU, and that gets cubed. If you notice, since I have the 1s on the bottom, this becomes a real easy problem. 12 squared is 144. Divided by 1, I can just leave that alone, equals d cubed. Now, if you look at the math button on your TI-80 calculator, when you hit the math, the fourth one down will be the cubed root of this. So I take the cube root of d cubed, and I get distance of Jupiter. And the cube root of 144 ends up giving me 5.24, and that's going to be AUs. So Jupiter is 5.24 AUs, or times farther from the sun than Earth is. And number 8, okay, before I go to number 8, let me talk about the homework. On the problems for the Kepler law problems, 37 and 37, you're just going to use the law of universal gravitation. On 41 through 44, we're going to use this formula here, but I'm going to look at 44 for a second. Because on 44, it tells you, instead of AUs, to use the distance from the moon. So instead of AUs, we're going to call these moon units. So when you're a moon or an MU, instead of doing the period of Earth, use the period of the moon for problem 44. So you would have 1 moon year. That's how long it takes the moon to go around the Earth. Okay, so you put a 1 in for the moon year. And over here for distance, you would use moon units instead of AU. So on number 4, I'll put 4. I'm at number 44. Use moon units for that, or how far away. And then the satellite's distance, it says it's half the distance to the moon. So you'd put in a 0.5 up here for the distance in moon units. And then you're going to solve it for how long does it take the satellite to go around in moon periods or moon years. On number 50, I'm going to give you another formula. You don't have to memorize this one for the test. This just tells you the speed. If I want to know the speed that a satellite's going around to orbit, here's the formula you can use. That big G, this would be the mass, and this would be the radius. So if I wanted to know the period of a orbiting satellite, that's 225 kilometers above the Earth. What we're going to do here is this. I'm going to take the square root. For G, I'm going to put in the 6.67 times 10 to the negative 11. For the mass, it's going to be the mass of Earth and then down here on the bottom, I'm going to put, sorry, my pen keeps not working, the radius or the distance that it is above the Earth. Now, see where it says 225 kilometers? I can't use kilometers, you got to use meters. So that'd be 225,000 meters. And then you do all that information there, and it will give you the velocity. So if I did this right, I should be having 42,000. Wow, that's awful fast. I don't know if I did that right. 42,068 meters per second. Actually, I know what I did wrong here. Let me erase the answer. What I did wrong is it says that it's 225 kilometers above the Earth. I forgot to add the radius of the Earth, because when you do the radius here, you have to remember it's from the center of the Earth. So we have to add the 6.38 times 10 to the 6th meters to that 225,000 meters. So when you take the square root of this whole thing, now you end up with 7,765, let's say, meters per second. So this one here is going to be like number 50A. And 50B, which you're going to use, is going to be like the second part of this one. So for 50B, I'm going to use another formula that says that the period is going to be equal to 2 times pi. Now you got to remember the period. Remember the formula, velocity equals distance over time. So if you cover up the time here, it's distance over velocity. Well, distance is going to be 2 pi r, so I'm going to put the 2 pi. Velocity is this equation up here. So I'm going to multiply that 2 pi by r cubed divided by big G and the mass of the Earth. I said cube. I meant cube, not square. R cubed. So when I put this in, I'm going to put 2 pi. The radius, don't forget, is this whole big thing down here. So it's going to be 225,000 plus 6.38 times 10 to the 6th meters. That whole big thing cubed divided by big G, which is 6.67 times 10 to the negative 11, times the mass of the Earth, which is 5.97 times 10 to the 24th. And then for that answer, we get a period of, in this case, that period would be 5,000, I don't get my pen to work, 5,344 seconds. And that gives you about 90 minutes. And that is about the speed that the space shuttle goes around, or the space station goes around the Earth, is about once every 90 minutes. So once again, that's the one to use for 50B. And if you want to do 51, let me show you a quick way to do that formula for 51A. Remember how F equals big G times M1 times M2 all over D squared? Well, 51A asks you to find the acceleration due to gravity. Well, if you remember, force of gravity is the same thing as mass times gravity. Okay? And so what ends up happening is this. One of these ends cancel out with one of these ends, so you're left with acceleration due to gravity on a planet is big G times the mass of the planet divided by the radius of the planet. So that's for 51A. And for B, naturally, you can just do the weight equals mass times gravity for that. Once you get this answer, plug it in down here. Okay? So that is the homework.